Okay. Then next is that star delta connection. In this case, the neutral is isolated. For star there is no neutral here, right. As the neutral is isolated, so 0 sequence current cannot flow, as and this side is delta, later we will see about next diagram we will see delta. So, it is star is that star side is your ungrounded, no ground. So, no 0 sequence current flow, and for delta you know there is no neutral, right. So, this will remain open, and this is your reference one. That means, these two diagram, this one that star grounded and other side secondary side is ungrounded, and this side and this one they are they have the same negative sequence diagram, this kind of connection, this one as well as this one. So, this will remain open because no negative sequence current can flow. When we will take the numericals for unbalanced fault, at that time we will see how things are connected. Now, another one is next one is that star grounded but delta connection. In this case what will happen, that neutral is grounded, that means primary current can flow because there is a 0 sequence circulation current in the delta connected secondary. That means, in this case a 0 sequence that your what you call circulating current can flow in the delta, but it will not leave it, right, it cannot leave the your terminal. So, in this I mean, so it will circulate, it will be circulating your 0 sequence current. So, in this case what will happen, that there is a 0 sequence circulating current in the delta connected secondary and a ground return path for the star connected primary. That means your neutral is grounded in this primary side, means this current can flow because there will be a your what you call that circulating current inside the delta, right. That means but in this case what will happen, that also note that no 0 sequence current can leave the delta terminal. So, it cannot leave the delta terminal because it is a circulating current. That means, this 0 sequence current can flow, if neutral is grounded primary side it can flow because the circulating 0 sequence current is there in delta. So, in that case what will happen, this is your 0 sequence reactance of the transformer, then you ground it, connect it, but as from delta, as it cannot leave the terminal 0 sequence current, it is circulating one. So, this will remain open, and this is your A dash, and this is your reference one. So, this little bit thing you have to understand this one. So, this side is grounded. So, primary circulating current will flow in delta, because in delta also 0 sequence circulating current will be there, but it cannot leave the delta your terminal, but it will be inside, it will be in circulating one. That is why, but primary current can flow because this side is grounded and this side your 0 sequence current can flow in primary side. That is why and delta it is a circulating 0 sequence current, but cannot leave the terminal. Therefore, that this your 0 sequence diagram for this connection will be make the transformer reactance, connect it to the reference, right, because at the beginning I said primary current can flow because there is 0 sequence circulate current in the delta connector. So, connect it, but after that this you leave open because this side delta the 0 sequence current cannot leave the delta terminal. So, this is your 0 sequence network diagram for this kind of connection. And another last one for this one, that another thing is that your delta connection, this is also delta, this is also delta. In this case what will happen, 0 sequence current will circulate in the delta, but it cannot leave the terminal. So, diagram should be right. So, delta terminal and equivalent circuit is that is a circulating current, this is delta, this is delta. So, this is line, this side will remain open, this side will remain open, but make a small loop, make the transformer 0 sequence your impedance and just close it like this. So, if you look this kind of diagram, when you I mean this kind of thing, this loop itself is isolated from this side or this side because it is a circulating current. So, for delta it will be a simply that you make it to the reference, but this will remain open. So, this is that 0 sequence diagram for delta. So, there are 5 such connections for transformer. These are very important for solving for your what you call when fault occurs, and this kind of this 0 sequence network is very important and it makes the things very simple. So, that is that means whatever we have said, the symmetrical component, positive, negative and 0 sequence, right. So, all these things more or less we have discussed, nothing has been left out actually. Now, let us take an example. It is example means is something like this. So, suppose you have a 3-phase balanced star connected load with self and mutual elements as shown in figure 6. The load neutral is grounded with Zn is equal to 0. That means, your this Zn reactance that it is taken as 0. You have to determine the sequence impedances. So, you have 3-phase your what balanced Y connected load, right. That means, that is your phase A, this is A, this is B and this is C. Voltage is VA, VB, VC and current flowing to this IA, IB, IC and reactance is ZS, 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 but they have a mutual inductance between phases, that means between phase A and B Zm, between phase B and C Zm and between phase A and C, that is also Zm, and this is your In, right, that neutral current. So, this is balanced Y connected load. So, you have to obtain that your sequence impedance. So, the line to ground voltage, because this is a from your circuit theory, your coupled circuit you have studied. So, the line to ground voltage VA will be equal to your VA will be equal to ZS IA plus Zm IB plus Zm your IC, because the mutual inductance is there. Therefore, you can write VA is equal to ZS IA plus Zm IB plus Zm IC, because mutual inductance is given between the phases. Similarly, your VB is equal to Zm IA plus Zs IB plus Zm IC, because we are writing for VB. So, Zs IB, other two will be Zm IA plus Zm IC. Similarly, when you write VC, Zs IC, then other two are Zm IA plus Zm IB. So, this way you write line to ground voltages VA, VB, VC. So, this equation you put in matrix form, that is VA, VB, VC equal to Zs, Zm, 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 Zs, Zm, 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 Zs. This is equation say 1. Now, we will follow the same your philosophy. This matrix as mutual inductance is there between the phases. So, this matrix will define ZABC, that is we know from the same relation that Vp is equal to ZABC IP, that is Vp is equal to, from this equation only, Vp is equal to VA VBC VC transpose, IP is equal to IA IBC IP IA IB IC transpose, and this is your ZABC matrix. So, Vp is equal to your VA VB VC transpose, IP is equal to IA IB IC transpose and ZABC is equal to this one. Therefore, same relationship we go back to equation 12, there Vp is equal to AVS and IP is equal to AIS. That means your Vp is equal to your AVS, same relationship equation 12, and IP is equal to AIS, same relationship, and this one Vp you put here your what you call Vp is equal to your, you put your AVS, your A into Vs, and here also IP is equal to put AIS. If you put that AVS will become ZABC into AIS, multiplying equation this 5 both side you multiply by A inverse. If you multiply by A inverse, then it will be VA1 VA2 VA0 is equal to 1/3, this is A inverse is equal to 1/3 this one, then this is your ZABC, this is your A, you know all these things we have given, and this is your IA1, IA2, IA0, multiply all. If you multiply, then what will happen, that this will become VA1 VA2 VA0 is equal to, it will become ZS minus Zm 0 0, it will become 0 ZS minus Zm 0, and it is 0 0 0 ZS plus 2 Zm IA1 IA2 IA0. This is equation 7, right, because here so many equations are there, 4, 5, 6 and previously also 2 and 3. Therefore, Z1 is equal to positive sequence will be Zs minus Zm, negative sequence also Zs minus Zm, and 0 sequence will become your Zs plus 2 Zm, right. So, next example is a delta connected resistive load So, this you have understood. Only thing is that just before that, only thing is that this multiplication you have to make it in correct way, because three matrix multiplications are there, and this beta operation you have to manipulate in a better way, such that you will get this correct answer. So, next is example 2. A delta connected resistive load is connected across an unbalanced 3-phase supply as shown in figure 7. I will give you that, show you that. Find the symmetrical components of line currents, also find the symmetrical components of the delta currents. Both you have to find out, symmetrical component of line current as well as your symmetrical component of this delta current. So, this example is like this. It is your diagram, it is a delta connection. Each branch it is resistive 3R, 3R and 3R taken. In phase A, current is 15 angle minus 60 degree ampere. In phase B, your 10 angle 30 degree ampere. So, current in C, current in here you can easily find it out IC, because IA plus IB plus IC is equal to 0. So, first what we will do is come to here, IA plus IB plus IC is equal to 0, IA is equal to given 15 angle minus 60 degree ampere, IB is given 10 angle 30 degree ampere. Therefore, 15 angle minus 60 plus 10 angle 30 plus IC is equal to 0. Therefore, IC will get 18 angle 154 degree ampere. So, 3 line currents you have got, and they are unbalanced. Now, using equation 24, 25 and 26, that 24 actually IA1 is equal to 1/3 IA plus beta IB plus beta square IC. So, it is 1/3, it is IA 15 angle minus 60, IB is equal to your 10 angle 30. So, it is multiplied by beta. So, it is 10 angle 120 degree plus 30 degree and plus 18 IC is angle 154 degree, 154 plus 240 degree. So, if you simplify this, you will get IA1 is equal to 4.64 angle 8.5 degree ampere. Only thing is that these calculations you have to make correctly. Sometimes I repeat that all these calculations actually were done by me. So, if there is any mistake in calculation or other things, just let me know. So, similarly IA2 is equal to 1/3, again that is from equation 25, this equation from equation 25, IA2 is equal to 1/3 IA plus beta square IB plus beta IC. Substitute all these values, that is IA2 is equal to 1/3 15 angle minus 60 degree plus 10 30 plus 240 degree plus 18 angle 154 degree plus 120 degree. So, IA2 will get 13.96 angle minus 77.9 degree ampere. Now, IA0 is equal to 1/3, you know, IA plus IB plus IC, and that is already that condition is given, because that delta connection it is IA plus IB plus IC is 0. Therefore, it is IA0 is equal to 0 ampere. Now, go to the your this is IA1, IA2, your IA0 we got. Now, go to IB1, IB2, IB0, IC1. So, we know that IB1 is equal to beta square IA1. So, we know this will become 4.64 to 48.5 degree ampere. We know IB2 is equal to beta IA2, that is 13.96 angle 42.1 degree ampere, and IB0 is equal to IA0 is equal to 0 ampere. Similarly, IC1 you can get now, IC1 is equal to beta IA1, you will get 4.64 angle 128.5 degree ampere. IC2 will get beta square IA2 13.96 and its angle is 162.1 degree ampere, and IC0 is equal to IA0 is equal to 0 ampere. So, we got IA1, IA2, IA0, we got IB1, IB2, IB0, we got IC1, IC2, IC0. Now, you have to find out something else, that is that this your delta load you convert it to star now. You have to convert this delta into star. So, that means, if you convert to star it will become RRR, because it is delta. So, it is given 3R, 3R, 3R. So, if you convert E star, then it is 3R into 3R divided by 3R plus 3R plus 3R. So, ultimately it will become R. That is why this is R, this is R and this is R, and current here is taken as IA, IB, IC, and voltage it is VAB, right. Similarly, VBC and VCA. So, in this case here your what you call, in this case if you this VAB is equal to, you can make in this loop say KVL. So, it is your IA into R minus IB into R is equal to VAB. That means, VAB is equal to RIA minus IAB, that is your IAB is equal to VAB upon 3R, right. So, your and this and sorry VAB is equal to R into IA minus. Now, IAB is equal to from here IAB is equal to this current going A to B. So, this current is IAB. So, IAB is equal to from this figure it is equal to VAB upon your what you call 3R. That means, this is actually I am for your as it is your this thing, it will help you in bracket I am writing actually it is from figure your 7, right, it is from figure 7. So, that means, IAB from this figure you can write that your VAB divided by 3R. So, that means, this VAB is equal to R into IA minus IB. Therefore, you put VAB here, that will be R into IA minus IB divided by 3R. That means, your RR will be cancelled and IAB will be 1/3 15 angle minus 60 degree, because IA is equal to 15 angle minus 60 degree and IB is equal to 10 angle 30 degree. So, minus 10 angle 30 degree. So, IAB you will get 6.01 angle 266.3 degree ampere. This is your IAB. Similar way you can compute IBC and ICA. So, IBC also the same, very easy to remember for this kind of thing, only 1/3 will be there IB as per the data taken. So, IBC is equal to 1/3 IB minus IC. So, 1/3 10 angle 30 minus IC is 18 angle 154 degree. It is coming IBC is equal to 8.33 angle minus 6.64 degree ampere. Similarly, ICA will be 1/3 ICA is equal to 1/3 IC minus IA is equal to 1/3 angle 18 angle 154 degree minus 15 angle minus 60 degree. So, ICA will be 10.5 to simplify angle 138.6 degree ampere. Now, this is IAB, IBC, ICA we have got. Now, go to the positive sequence, negative sequence and your 0 sequence component current say for say IAB. So, same philosophy, same formula. So, IAB1 we will write 1/3 because we have got IAB, IBC, ICA we have got it. Now, IAB1 that is positive sequence component current of the line AB. So, that is IAB1 is equal to 1/3 IAB plus beta IBC plus beta square ICA. So, you substitute all these values. So, IAB is equal to 1/3 IAB 6.01 angle 266.3 degree plus 8.33 your it is your IBC what that is 8.33 angle minus 6.64 degree, but beta. So, 120 degree minus 6.64 degree plus your beta square ICA. Beta square ICA actually ICA is equal to 138.6 degree, right, and with that beta square means 240. So, 10.5 angle 378.6 degree. So, if you simplify IAB1 that will become your 2.67 angle 38.5 degree ampere. Similarly, IAB2 is equal to 1/3 IAB plus beta square IBC plus beta ICA. I give you please do this one, you substitute IAB, IBC, ICA and beta square and beta all these angles and please simplify, you will get IAB2 is equal to 8.06 angle minus 107.9 degree ampere and IAB0 will be 1/3 IAB plus IBC plus ICA, IAB0 will become 0. Also note that you can verify that IAB1 we actually use IA1 by root 3 angle 30 degree. You know IA1, you substitute here divide by root this thing root 3, you will see this is becoming actually IAB1 is equal to and root 3 30 degree. Similarly, here also IAB2 will become IA2 by root 3 angle minus 30 degree. Actually, this holds. So, this is I have just written in brackets. This is the that means that your IAB1 and your this is that positive synchronous component of your phase current your this thing what you call phase A, right. So, this relationship holds. So, this is that only thing is that you have to compute thing correctly and you have to remember certain things. Now, slowly and slowly we will see something else. Now, another one is these are problem type, at the same time you know how things can be done. For example, you have a delta connected load, right, and 3 phase supply, it is a 3 phase supply ABC, and it is a current of P and supplying a current of 15 ampere, right. But if the fuse in one of the lines melts, actually it is a then compute the symmetrical component of the current. So, I mean one of the line that suppose it is cut, fuse melts, that means gone, that means IB will become 0. So, what will happen? So, in that case if this is 0, but current is given, just mention 15 ampere. So, in that case suppose I A is equal to, we take 15 angle 0 that ampere reference one, then IB is 0, that means this I A and this I C also, because there is no current here, that means this is the path for I C, that means your I C that I A is equal to then minus I C. So, in this case I B is equal to 0, therefore, I C minus I C means I C is equal to 15 angle 180 degree ampere. So, we know that relationship I A 1 is equal to 1/3 I A plus beta I C plus beta square I B. So, you substitute all these values I A, I B, I C is anyway 0, right, and beta that angle. So, you will get I A 1 is equal to 7.5 plus j 4.33 ampere. Now, similarly, I A 2 if you calculate, it is 1/3 I A plus beta square I C plus beta I B, again I A, I B, I C you substitute and beta is there, accordingly you make the angle, put this angle. So, it will be 7.5 minus j 4.33 ampere, and I A 0 will become 1/3 I A plus I B plus I C, that is 0. That means, I A is equal to, for cross check, I A is equal to I A 1 plus I A 2 plus I A 0. I A 0 is 0, that means, I A is equal to I A 1 plus I A 2. So, I A 1 is equal to this much plus this much. So, minus j 4.33 plus j 4.3 will cancel, ultimately I A will become 15 angle 0. So, for a cross check, this is a simple problem, but it is a good problem. Next one, whatever will show that we have studied that altogether per unit system, that this problem itself is a whole page, but not that difficult one, but 0 sequence thing, that whole page, this problem is like this. Then I will explain. The question is that for per unit system, that we have taken a particular base, and accordingly all base of your base voltages of the line as well as the generator or transformer, whatever it is, accordingly it has been changed. So, those things we have studied in that your per unit system, and here for this problem we need those formulas, right. First we have to convert it to that old base impedance, and then with the new base you convert it to per unit. So, this example directly I will write it, because per unit system component, as far as I remember, everything has been given and many problems have been solved. So, this one, before giving the diagram, is a very big problem, but just read carefully, that diagram will be given. So, things will be easier. So, a 50 MVA 11 kV synchronous generator, I will show you the diagram, has a subtransient reactance of 20%. The generator supplies 2 motors over a transmission line with transformers at both ends as shown in figure 9. I will come to that. The motors have rated inputs of 30 and 50 MVA, both 10 kV with 25% subtransient reactance. The 3 phase transformers are both rated 60 MVA 10.8/121 kV with leakage reactance of 10%. This is the per unit. Assume 0 sequence reactances for the generator and motors of 6% each. Current limiting reactors of 2.5 ohm each are connected in the neutral of the generator and motor number 2. There are 2 motors, so it is motor number 2. The 0 sequence reactance of both transmission line is 300 ohm. The series reactance of the line is 100 ohm. So, draw the positive, negative and 0 sequence network. Positive, once you get all the parameters, positive and negative sequence is not at all a problem, problem is that 0 sequence, right. I mean, you have to make it very carefully. So, this is actually some assumption, that assume that the negative sequence reactance of each machine is equal to its half transient reactance, that is also given. So, this is the diagram. You have a generator generator actually grounded, star connected and grounded. This is transformer T1, this is your delta star transformer, star side is grounded. This is transformer T2, star delta, here also star side is grounded. Here also your motor 1, this is actually motors, this is motor 1, here is star but no ground, and this is motor 2, it is 2 is written in the bracket in the circle inside the circle, here also I have written 1, and here it is this motor is grounded, right. So, now when you will do, when you will solve such kind of problems for such that you will not make any mistake or anything when you will calculate, you mark some point, for example, this is D, you can put a bus bar like a thing also, no problem. Then you can make this is E and F, this is the line actually, this is actually your line, that is transmission line, and this is this F. Here also we can mark by a point. I have made D E your P Q, and this point I have not marked it, and if I have marked I will show you later in the diagram, right. And this point is P and Q. This way first you mark it, every place you mark it, right. Then you will find things will be, perhaps it will be easier for you. So, you have to draw positive, negative and zero sequence diagram. Once you get the parameters, positive and negative is not at all a problem. So, only thing is zero sequence you have to understand little bit. So, assume base power is equal to 50 MVA and base voltage 11 kV, because the generator actually given 50 MVA 11 kV. So, what we are doing is that we are actually assuming base power 50 MVA and base voltage 11 kV, right. So, now base voltage of transmission line, then it will be 11 into 121 by 10.8 kV, because this transformer side actually it is your 10.8 121 kV. So, that is why that base will change for the line side, it will be 11 into 121 10.8, because transformer actually this is your 10.8 by 121 kV. So, it is 11 into 121 by 10.8. So, that is the line your base voltage 123.2 kV. Now, motor base voltage, again you have to go to this is the line, right. This transformer again 10.8 by your this thing 121. So, again it will be 123.2 into 10.8 by 121. So, motor side again will become 11 kV. This all we have seen for per unit thing. I hope you will understand this. So, transformer reactance, so both are given X T1, X2, this is given 10%, right. Now, what we have to do is that same that per unit system, I have not written which equation number it is, but idea is that first this is your what you call the transformer is 60 MVA, that is your both the transformer rating is given. Let me see where this data are given, that your here have I written, no, here it is given that the motors are rated at this and transformers your the 3 phase transformer both 60 MVA, right, and rated at 10.8 121 kV. So, that means this transformer rate, this per unit impedance is given 0.1, right. So, first is the transformer base, the base impedance is 60 upon 10 your what you call that 10.8 square by 60. So, with that if you multiply, this will be the origin, that is 10.8 square by 60 is there, with that you multiply, that is its a ohmic value in its own base. Now, we have taken 50 MVA base and 11 kV. So, we have to divide by that 11 square by 50. So, that is why it is coming 0.1 into 50 upon 60 into 10.8 upon 11 whole square, that gives 0.0805 per unit. This old your old base and new base of MVA as well as voltages, that in per unit system details are given. So, the details are given. So, from there only I am writing, right. So, this way X T1 X T2 you will get 0.0805 per unit. Thank you, again welcome.